Okay, so the first example that your book does is the example of the electric field of a charged disk. So imagine we've got a wire or some kind of linear object that has a total charge Q, and we're located some distance x on the axis of that disk. And we want to find the electric field at this point in space. Notice that we could use the expression that we just talked about, that the electric field is just equal to the integral of all the bits of electric field, which is equal to the integral of 1 over 4 pi epsilon 0 dq over r squared. We could use that to find the electric field at any point in space. If we had a disk of charge and we were over here, we could find the electric field at that point using that equation. But notice that if I'm at that point in space, first of all, the direction of the electric field is kind of complicated. It's not in a straight line. It has both horizontal and vertical components. Also notice that my distance from the different parts of the disk is not all the same. So this integral in that case would actually be pretty hard to do. In this chapter we're going to deal with situations where the symmetry of the problem lends itself to a simple integral. Notice that if we are on the axis of the disk, if we're at a point above the axis, that we're the same distance away from every point on the disk. So this radial distance is a constant. Also notice that the components of the force or the electric field that's going to be exerted at this point cancel one another out in the horizontal direction, or in the, we call this the x-axis, in the y direction, because this piece of the ring exerts a force in that direction, and this piece of the ring exerts a force in that direction, and the components in the y direction are going to be equal, so they cancel one another out. So the first step we usually take in these problems is to look at the symmetry of the situation, to ask ourselves, what can we ignore? In this case, we can ignore what your diagram in your book calls the perpendicular component of the electric field, and only consider the horizontal component of the electric field, the x component of the electric field. So we can write right off the bat that the electric field at this point in space is equal to the integral of the electric field due to each little bit of the ring, but we only need to consider the horizontal component of that. So we only need to add up the horizontal bits of the electric field, and that turns our vector equation into just a scalar equation. We only need to consider one component. So we can write this as 1 over 4 pi epsilon naught the integral of dq over r squared, where dq is every little bit of charge that contributes to the electric field, times the cosine of theta. What is dq in this situation? dq is just a little element, a little slice of this arc. So every little bit of this arc has a length equal to a times this angle. We're just calling that for now dl. We don't need to get any fancier than that. And so the charge of this is equal to the charge density times dl. In this chapter, we'll usually be using, when we have a charge per unit length, we'll use lambda. So lambda is the total charge of this thing divided by the total length of this thing, which is 2 pi a. So we'll call that the linear charge density. In situations where you've got an area of charge, we'll usually use a sigma to stand for that. In situations where you've got a three-dimensional object, a volume of charge, we'll usually use rho to stand for the charge per unit volume. So that's just a convention we use. We use different symbols for density, whether it's a linear density or an area density or a volume density. So the charge density of this is equal to the total charge divided by the total length, which is just 2 pi a, the circumference of the ring. So we can write this is equal to 1 over 4 pi epsilon 0. dq is lambda dl over r squared. This is an integral times cosine theta, which is equal to, get this out of the way, 1 over 4 pi epsilon naught. What do I want to write this in terms of? I could leave it lambda, but I'm going to actually write that in terms of the charge over the circumference. So lambda is q over 2 pi a times 1 over r squared cosine theta dl. Now, what are our limits of integration? Our limits of integration are around the circle. The thing we're integrating is we're integrating around this loop. But if we look at what we have here in our integrand, well, let's write cosine theta in terms of things we know too. This is 1 over 4 pi epsilon 0 q over 2 pi a integral of 1 over r squared. And what is cosine theta? Cosine theta is just x over r. So we can write this as times x over r dl. Notice that as we integrate around this loop, r is a constant. The distance from this point on the axis to any point on the loop is always the same. X is a constant. The distance from the center of the loop to our point is constant. So none of these variables are actually variable. Okay? We can write that this is equal to 1 over 4 pi epsilon naught q over 2 pi a 1 over r cubed times x times the integral of dl. The integral of dl is just the length of that loop, or the circumference of that loop, which is just 2 pi a, which cancels that 2 pi a. So what we have is 1 over 4 pi epsilon naught q, write it there, times x over r cubed. If we want to express this answer in terms of the kind of simple relevant quantities in the program, or in the problem, x is the distance from the center of the disk to our point. R is the distance from the edge of the disk to our point. We probably want to express everything in terms of x and a. So we can just write r just geometrically as the hypotenuse of that triangle, right? So r is equal to the square root of x squared plus a squared. So our final answer looks something like this. 1 over 4 pi epsilon naught qx over the square root of x squared plus a squared cubed. So we can write that as x squared plus a squared to the 3/2. And if we want to specify that this is in the x direction, we can add a unit vector there. Okay, so this is our electric field, 1 over 4 pi epsilon naught. The charge of the ring times their distance from the ring divided by q x squared plus a squared to the 3/2 power. How do we know if that's right? That's a pretty ugly result for such a seemingly simple problem. Remember that one of the things we like to do all the time when we get an answer like this is to check it in various limiting situations. The limiting situation we want to do in this is if we imagine a ring of charge, and we want to ask ourselves, well, what's the, we've got a ring, oops, we've got a ring of charge, radius A, and we're some distance x away from it, and this has a charge q. What's an interesting limiting case we could look at? Well, one interesting limiting case we could look at is the limit of this expression as the radius of the ring goes to 0. What is the limit of this expression as a goes to 0? Well, it's, let me change colors here. If that goes to 0, this is just 1 over 4 pi epsilon naught q times x over x squared to the 3/2, which is x cubed, and that's just equal to q over x squared. And that, 1 over 4 pi epsilon naught times the charge divided by the distance squared, is just the electric field you would expect from a point particle, which is exactly what you get if you take a ring and you shrink it down to 0. So not only does this answer make sense, it reduces to the expression you would expect for a point charge located a distance x away from you. Okay? We will actually use this result a couple times in finding the electric fields of other objects. So file this expression away, 1 over 4 pi epsilon naught, the charge times the distance divided by x squared plus a squared to the 3/2, because we will see it again.